All right, works.
Wasn't there any meat stuff on there? Because I actually, basically, no, Mommy, I'm happy you said that because now if I find anything a bit mixed up, and the sharp knives and.
Yeah, these, the ones on the set have this.
Yeah, that's what I worked out. And then I stuck that in there, the plates, and then I put just the glasses in there. So if anything's missing, I just put it in one place. And the mugs up there. I was going to get hand towel in here.
I looked for
Choco! No, the powdered one. Why don't you put a piece of paper now, Choco, and there's one other thing you just said. What did you just ask for?
Ices?
Yeah, no, something else.
I went into the hardware store and tried to get a kettle. They only had a tiny one, this big. They didn't have a tube for the dryer.
Okay.
Keep something.
Oh, it does? I haven't noticed.
Yeah, I keep them working out. Oh, I've got class. And recording. Okay. Okay. So single precision. No, doesn't let me do that. Okay. Single precision floating. So what we're going to talk about now is how to represent a number, a float, particularly, not a integer, in the computer. Now, I say in the computer because you already learned in the course on digital systems a little bit about how to represent a floating point number. So, but you didn't learn exactly how it's done in the computer. Now, of course, the computer, every computer can be different. We're going to learn how it's done in the MIPS, but they all, probably work in the same way. I mean, I can't vouch for every single computer in the world, but basically they work in this way. First, let me explain something about general scientific notation. You guys may already know this, but maybe you don't. Scientific notation is a way of representing numbers that are very large or very small by expressing them as a small decimal times 10 to a power. So for example, I could have the number, let's start with something simple, 15.67, and I can also represent it as 1.567 times 10 to the first, because if I multiply that times 10 to the first, which I essentially add a 0, I multiply it by 10, and I get 15.67. So I can also represent, for another example, let's say I have 5,600 and, actually that's, I put the comma in the wrong place. Well, let's say there, 5,612 times 10 to the third is 1,000, right? 10 to the third is 1,000. So that becomes 5,600. And notice I dropped off the 2. It depends how accurate I want to be. I can write the 2. Oh, sorry. I can write the 2 over here, and then I do it exactly. Sometimes we have a very large number, like, the distance from here to the sun, in kilometers or something, so, or in meters. So it'll be a very large number. I may end up having like something like this, I don't know. Something like that, in which case I can represent it. This is 9 zeros, so I can represent it like that. And here I can be inaccurate because I'm, not exactly interested in exactly how many kilometers. I want to know the more or less how much it is. So it's 10 to what we say is the order of magnitude, 10 to the 12th. So too, I can have the number a third. I could, well, that's something else. That's not relevant to us, really. Okay, so far so good?
Yeah.
Okay. Now, where Yitz, you sent to everybody?
Yeah, it's on the group.
Where? In WhatsApp?
Yeah.
Okay. And what else? Also, I said I put up some videos. I don't know if you saw for the lab. Are you in the lab you're in the lab with me, right? Did anybody see the videos for the lab?
I saw the videos in the lab.
Okay, good. So yeah, I put up videos like a guide for 1 point. If you look at Moodle, there's videos for up to lab 1.1, 1.2, 2.1, 2.2, and 3.1. All those, which should keep you busy for a while. I have videos. I basically do have to work for you or more. So if you don't want to, don't look at them, and then you'll figure it out yourself. But if you're having trouble, you can look at my video guides. Now, give me some feedback if you like them or if you need some improvement. Okay. Now I could also have a number that is a decimal number. I mean a binary number. And I didn't count exactly. Let's say I have this very large binary number. I can also represent it as 1.010101, etc., etc. I don't have to do all of the accuracy, just sometimes 2 to the, let's say 37. I didn't count, but assuming they're like 37 zeros here, then 37 digits here, then after the 1, then that would be 37. Now, and it would be times 2 to the 10 because it's binary. Every digit here is times 2. So that would be the representation. Now, if I had, let's go back over here, and let's say I had 0, 0. I would still represent this number as the same way, because the zeros in front don't change the number in any way. So to over here, if I had, 0, 0, 0, which is possible because, we always fill, if we have a byte, if we have a 32-bit word, we might have, 32 numbers. And so even though we have a 1 somewhere, we have zeros on the left of it. So how do we represent it? So basically we ignore, just like we ignore the zeros here, we ignore the zeros here, we go straight to the first one. So it'll be, we ignore those, and then we start with the 1, and then we count how many numbers are after the decimal point, and that's our power of our 2. And we're actually going to see that we'll always stop at the first 1. So theoretically, we could get rid of this 1. Because, well, I'll tell you like this. First of all, I want to say something more about scientific notation. It's always represented as 1 digit to the left of the decimal point. Never 2. You would never write it wouldn't be scientific notation to write this, 15 times 10 to the 0, even though it's correct. There's times 10 to the 0. That is correct. But we would never do that because, not because we don't like 10 to the 0, but because we don't like this 2 digits to the left of the point. We always go to 1 digit. So too over here, we're always going to go to 1 digit. Now that 1 digit will always be a 1. So we don't actually have to write it. We can save bits and just not write it. We can just write 0.0. Oh, I got in very small letters here. 0.01010101 times 2 to the 37th. Any questions so far?
In this case, you could have moved it even further to the left and then did 2 to the 39.
No. Because I need to have, no, basically what I do is like this. There's a two-step process. I take the zeros that are here and I ignore them. And I get to the 1. And then I write it, and that's my answer. But then we're going to see that on the computer, in order to save space, we're just never going to write this 1 because it's always going to be a 1 there. We just know that there'll be a 1 there. We can't keep moving the point. We can't go to the next one and then drop that one, and then we'll end up having nothing left. In other words, this is equivalent to this because, or did I wrote too many. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Yeah, this, I wrote too many. These are equivalent. I just didn't, I was just lazy and I didn't write the 1 here because I know there'll be a 1. Every number, in other words, just like every number in that's base 10 in scientific notation will start with a single digit, either a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. It was base 10. So too, I know that every number in binary will either be a 0 or a 1, but it'll never be a 0 because there's no point in writing 0 point something. I can always go to the, I'll just move it over and I'll go to the 1. So since I'll always write it with a 1 at the beginning, I can just sort of write blank like that. And just have like inferred, and just infer when I see the number that I have to have a 1 over there. You understand? I can't keep going.
Yeah, thanks.
All right, now let's go to the next slide. So now what we do is, well, first of all, some names. We call this the mantissa, and we call this the exponent. Now we're going to ask a question. Now we're not going to actually, if we're going to represent this in the computer, we're not going to represent the 2. We're just going to represent these ones, the mantissa and the exponent. And then we have to ask the question, how many bits of the 32 bits in our word are we going to use for the purpose of representing these numbers? So that's what this next slide is. We use 8 bits for the exponent, 23 bits for the mantissa, and 1 bit for the sign. That's how we're going to break it up. So in other words, if I go skip ahead here, without understanding this whole slide here, but just look, I have the framework of my 32 bits. 23 plus 8 is 31, plus 1 is 32. So these are my 32 bits, and how are they broken up? The mantissa takes up this framework, this area, 23 bits. The exponent takes up this area, 8 bits, and the sign, whether it's positive or negative, is just 1 bit. In other words, I don't do what we call sign extension. I just write a single bit for the sign. This is not going to be in the shita that you learn, in the method that you learned called 2's complement. We're going to actually write the number in, whether it's positive or negative, we're going to write it as a positive number, and then we're just going to have a sign bit. A lot easier, actually.
It's like sign and magnitude?
Exactly, sign and magnitude. Well,
What is
sign,
mantissa?
mantissa is this part. That's called the mantissa.
Okay, after the decimal.
No, well, this is also the mantissa. Mantissa is a general term in math for the thing that you bring to the power. That is the thing that is multiplied by the exponent. I mean, not the 10, but the values. So it would be here this, and it would be here this, and it would be here this, including the implied 1. But that's technically called, but in reality, we're not going to write that 1, and we're not going to write the dot either. We're just going to write this. So that'll be our mantissa with an implied 1. So that's going to be 23 bits, is what I'm saying over here. We're going to have 23 bits for accuracy. In other words, for the accuracy, and then we have the power, which will be 8 bits. So that means like the maximum, if you think about 8 bits is a byte. And we know that a byte maximum value is plus or minus 127 or 8. So you'll be able to raise some number to approximately to the power 2 to the power 127, which is quite large. But that's our limit. We have a limit. Now we're going to do an example. And the example is to take a number like 44.5 and convert it into binary and then represent it in our computer. So this process you should have learned how to do this in digital systems, but I'm going to do it again with you. Did you guys learn it?
Yeah, we did.
Yeah, we did. Okay, good. So if you learned it then, this will just be review. If you don't remember it, if you didn't learn it or you should have learned it, but now we'll learn it for the first time. So it's pretty simple. Convert the left-hand side of the number to binary. So first we take the 45, we want to convert it to binary. So how do we do it? Basically, we take the 45 and we divide it by 2, and we get 22. So 22, it would be correct to say that 22 times 2 plus 1 is 45. And that's true. Because when we divided this by 2, we had a remainder of 1, right? We did, this goes into 44 22 times. I'm going to say 2. We divide this by 2. So 22 goes into 45 22 times with a remainder of 1. So we write the remainder of 1, and remember that 22, which is how many times the 2 went in. Then we take again the 22 and divide it by 2. And we say, that'll give us 11 with a remainder of 0. And then we're going to take that 11 and divide it by 2 and get 5. And 5 we'll divide it by 2, we'll get 5, and we'll have a remainder of 1. And we keep doing this until we get, let's say, 2 divided by 2 is 1 with a remainder of 0. Now we have 1 left over. 1 divided by 2 is 0. In other words, 1 divided by 2 is a half, but 1 divided by 2 in integers is a 0 with a remainder of 1. Once we've gotten down to the point where we have 0 as our result, then we're done. Then we just write the remainder and we're done. There's no more purpose of going on. So we take our number and we divide it by 2 until we get to 0. Until what we've gotten 1. 1 is not the end. Got to divide 1 by 2 and get 0. And now we've got the end. Now we look at this number and we read it from bottom up, not from top down, and we get 1 0 1 1 0 1. And that is what we have over here, and we write that. That's
Why do we read it from bottom up?
What?
Why do we read it from bottom up?
Well, if you think about it, because, why do we read it from bottom up? It's a good question. I mean, this example actually is a palindrome, so it doesn't matter which way we read it. But if we had a different answer, let's do another one.
It makes sense for the first one, that the top one becomes the last one, because that's the remainder.
That's the remainder of the whole number. In other words, if we would have a 0 here, that's obviously the digit. That's this 1 over here, because that's telling us we need to add 1 to it. I mean,
that's the only one I understand. I don't know how to understand the rest.
Once you get that, then it all follows. Once that one is true, then it all follows. But we can do another example that's different. Let me add a slide. Let's say we had 46. 46 divided by 2 is what?
23.
23, remainder 0. Now 23 divided by 2 is 11, remainder 1. True?
True.
11 divided by, well, now all of a sudden, first of all, we see that this 0 is not going to be at the left-hand side, because then it would be irrelevant. This 0, if it would be at the left-hand side, it would be irrelevant. It's going to be on the right-hand side. And it's, well, we'll see. Let's just keep going. 11 divided by 2. So we have 11 now. 11 divided by 2 is 5, remainder 1. And when we have 5 divided by 2 is 2, and we have remainder 1. True? stop me if I make a mistake.
Okay.
So far, so good. Now we have 2 divided by 2 is 1, remainder 0. Just checking myself. Okay. And now we have 1 divided by 2 is a half, which means it's 0, remainder 1. By the way, logically, we should always end up with a 1 at the end, shouldn't we? Because,
Well, you can't not have a 1 there, because if it was a 0, then you wouldn't consider it in the first place.
right,
So
exactly.
it has to end with a 1.
You have to end with a 1, which makes sense that would be the most significant bit, because obviously you're not going to start off with a 0 on the left side, because that would be meaningless. So you wouldn't want it there. So that's clearly going to be the most significant bit, that 1. And you'll always have a 1 there.
One
So
way
now
to think about it is that when you keep dividing by 2, you keep chopping off the last bit, the rightmost bit. So when you have 46, you're chopping off the last 0, and then it's divided by 2, so you have 23, and you chop off the 1 and keep going down.
Agreed. And then 1, 1, 0. Now, that number is not a palindrome. So we can look at it and we can say, well, this is a, sorry, let me just go like this.
It's 14 plus 32, which is 46.
Yeah, well, let me do that again with you guys. So it's, oh, wait, I want to do it like this. Sorry. Single and, okay. So we have, yeah, you're saying this is 32, sorry, this is 32, and then this would be 16, and then this would be 8, and then this would be 4, and then 2, and then no 1. So 32 and 8 is 40, plus 6 is 46. So that's 46. But it only worked if we did it that way. So first of all, I'm just proving that you do have to do it from the top up, because otherwise it won't work. That's just the most basic thing. That's why it works. And it makes sense however you want to think about it. I don't need to think about it too much, but yeah, it makes sense. So it's from the bottom up. So that was just to prove it, because I didn't like this example because it's palindrome. Doesn't matter which way. Doesn't prove it. Okay, so now convert the decimal part to a binary part. So remember, it was 45.45. So we got to do the 0.45 now. That's going to be different. So we take 40.45 and we multiply it by 2, and we get 0.9. And 0.9 is, we're going to go over here. We have 0.9 times 2, we get 18, or 1.8. Now 1.8, we're going to ignore the 1 and take the 8 and put it over here, and 0.8 times 2 and get 16. Now again, we're going to ignore the 1 and just take the 0.6, just like we actually ignored the 0 here. But we're always going to put a 0. We're always going to ignore what's on the left of the point. So 6 is going to come over here. 6 times 2 is 12, or 6, 1.2. 6.6 times 2 is 1.2. And again, we're going to leave the 1 there and just take the 2 over. 0.2 times 2 is 0.4, and we're going to take the 0.4 and multiply it. And we can keep actually going. If you notice, we've got the 0.08. 0.08 is the same as, is here, is 0.08. We're going to put this 0.08 over here, and times 2, we're going to get 16 again. And then we're going to get a 6 here, and then we're going to get 12 again, and then we're going to get 4, and then 8. And we're going to go forever. So I put this in yellow background to indicate that those are repeating forever. We'll get into an infinite loop here if we keep our process going. Once we recognize, we don't always have an infinite loop. If it would be, I don't know, something else, it would end perhaps. But here, if we notice an infinite loop, then we know we can stop. I mean, if we get to 0, if we get to like 0 times 2, then obviously we're done, because 0 times 2 is 0, and we're just going to get a lot of zeros, so we don't have to write those, so we're done then. So if we get to 0, if we don't get to 0, then we should look for an infinite loop.
In digital
And-
systems, we were taught that we could stop after 5 digits. Is that different here?
That is different here. That is different here. You can stop after 23 digits. That is what, oh, sorry. That is what I mean over here when I say the mantissa is 23 digits. In other words, we need to have 23 digits, but we're going to stop at this infinite loop. We can stop our process here, and we'll remember that it's infinite, and we'll read it now from top to bottom, 0, 1, 1, 1, 0, 0, 0, 1, 1, 0, 0, and the 1, 1, 0, 0 is, I put an underline under it to indicate that it's repeating, because I couldn't do an overline in slides, in Google Slides. But imagine that's an overline, but it's underlined, it means it's repeating. So now we have our, so far we have this 1, 0, 1, 1, 0, 1, that's our palindrome. And then the new thing we got 0, 1, 1, 1, 0, 0, and that repeats. So if we're going to put this into scientific notation, we are going to have to move the decimal point, because this decimal point is over here. It should be, only one digit should be to the left of the decimal point, and it should dafka be a 1. So we're going to go all the way to here and put a 1 there. So we're going to do it 1.0110101. But since we moved it 1, 2, 3, 4, 5 places, it's going to be times 2 to the 5th. So now we can start talking about what to write in this box, in this frame. We can say that the sign is 0 because it was a positive number. We don't have to worry about mashlim l'shtayim. We don't have to worry about 2's complement. And the exponent is going to be, well, without talking about it too much, but let's just say it's 5. How we're going to represent 5, we're going to see in a minute. But let's say our exponent is 5. And our mantissa is everything but excluding the 1, because that's going to be implied. So where the mantissa is going to be 0, 1, 1, 0, 1, 0, 1, 1. And we're going to write it here, but we drop off the leading 1. That's what I said. And we're going to write this here, but that's not going to take up all 23 bits. So how far should we go? So if you look, so actually what we're going to do is we're going to take these 4 bits, and we're going to, since they're repeating, we're going to keep repeating them. And we're going to fill up this 23-bit space until we can't write anymore. In other words, this will not be our mantissa. Our mantissa will be this, with an additional 12 digits of 1, 0, oh sorry, 1, 1, 0, 0. So it'll be another 4 of them, I think. 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, etc. So we can fill up all 23. Because we want as much accuracy as possible. No reason not to. If we would just write zeros, then we would lose some accuracy. Now I want to explain, now I got a whole slide about explaining how to write this 5 over here. You could say, well, just write 5 over here. Well, one way of doing, but we want to have also negative powers. We want to be able to say that this number is actually, like if we're measuring, for example, the size of the of an electron, or I don't know, the size of a proton, we would have to have a very small number. So we'd be like to the negative power, be like, you know, very tiny number of meters it is across. So this number could have a negative power. So the power here can be negative or positive. So we have a choice. We could have theoretically put it in 2's complement, but instead of doing 2's complement, we did a different system. Or, you know, generally it's done a different system. Instead of using 2's complement, we're going to use something else called, well, I think we called it like power and sign, something like that. Did you guys learn something like that before you learned 2's complement?
Yeah, it was sign and magnitude. Is what we call
Sign
it.
and magnitude. So that's what we're going to do now. So what we're going to do is we're going to write the magnitude, but we're going to do a special. So we have the sign. Sorry, here's the sign, and here's the accuracy, and here's the magnitude or the power. I would call that the magnitude. But we're going to write it in a funny system. First of all, here's like this. We have 8 bits for it. That's a byte. We know that the number of combinations, where we know the largest value is 255. It goes from 0 to 255. And we're just going to divide that group in half. and say that the whole upper half is the positive numbers and the whole lower half is the negative numbers. Again, we're going to say like 255 is going to be the positive numbers, but when we get to like 128 or 126, it's going to start being the negative numbers. In other words, we're going to use positive numbers to represent negative numbers. We're going to say that this range of 255, from 0 to 255, we're going to divide the range in half and say that the larger numbers there are going to be positive and the smaller numbers there, which are positive numbers, but they're going to be representing negative numbers. So another way of saying that is we're just going to take whatever number we put there and subtract 127 from it. So in other words, if I would write 11111, all ones in the 8 bits, which is normally 255, I'm going to subtract from it 127 and get 128. And that will mean, if I write all ones there, that means I'm raising it 2 to the power 128. And that's the largest value that I could raise it to. And the smallest value I could raise it to would be 0. But 0 would actually be 0 minus 127, so it would be equal to 100 minus 127. That's just the way they chose to do it. Doesn't really matter why. Okay?
Could it be because now we have an extra one on the positive side instead of the negative side?
I
Because
thought I had that
complement-
exact same thought. Perhaps it's because we prefer to have one extra positive. But there might be other reasons for it too, which we're about to see, I think. I don't know. You can think about if we would have faced certain problems if we hadn't done it this way. Because we're about to talk about a problem. But that could be. That's a perfectly reasonable thing to say. We wanted to have a little bit more positive numbers because we more often use positive numbers. But they could just say they just chose this way because they didn't, for 8 bits, they didn't want to start doing much, 2's complement. Just simpler, maybe. Anyway, so to represent, really the question is, why don't we use this system always? Why do we use 2's complement? I think because it has some benefits in math computations. But I don't know. I haven't really thought about that too much. Anyway, so to represent 5, we need to add. So if let's say we want to do 5. So that's our example, right? We had gotten our example. The exponent was 5 here. The sign was 0. The exponent was 5, and the mantissa was this number. So how are we going to represent that 5 in binary? In binary in this system. So we're going to say, well, since he's going to take away 127 from it, let's write 132. And when he takes 27 away from it, we'll get 5. So we're going to write this number, which is 132, I think.
I think the first one brings us to 1. The first bit gets us all the way up to 1, and then that bit is 4. So I think it gets us to 5. I think that's the way it works.
You're saying instead of doing the math, you can just have a system, and you're saying like this. This 1 represents 1. And then this one here is 4, but it's really 5 because of this 1.
Well, I'm saying the first row is when it's all 0,
the ones.
negative 127. So we add 128.
I understand.
What was the first one add?
Well, first of all, we don't need to get into
100 brings us to 1, and then we just add another 4.
I think what you said is very insightful, but and I think it is. I think you're right, but I just want to say it simpler. This is the value 132 because a 1 here is 128, and this is a 4. 128 plus 4 is 132. That just is the value. That's just how I write 132. In other words, I did the math. I said, what's 5 plus 127? And I got 132, and then I wrote 132, and that's it, and I'm done. I don't need to think about anything else. Now, what you're saying is you're making an observation, which is to say, the 1 here means that it would be power 1. Well, that's true. And then I just have to write the 4 to get me up to 5, and that's what I did. And that's right. Anyway, and this will be our exponent. So so basically we write a 0 here to tell us it's positive. We write 132 here to mean that 5. And we write that mantissa, but notice I added 0, 1, 1, 0, 1, 1, 0, 0, and then I didn't have room for two more digits. So I had to stop there because I ran out. I had only 23 bits to write here. So that's our 32-bit expression of 45.45. And now an interesting observation is, remember to repeat the last 4 digits until you use other. An interesting observation is that, just a side point, is that 45.45 is fully represented. I have represented 45.45 fully. It is an accurate representation of that number when I write 45.45. There's nothing missing. But when I convert that number into binary, this number is not
And you
exactly.
have to repeat the last 4 digits. It's always going to be the last 4 digits.
I'm going to, no. Some numbers, when I convert them, will be repeating 6 digits. Some will be repeating 3 digits. Anything is possible. You have to recognize when it starts returning on itself. I mean, I don't know if anything is possible, but no, there's no rule that it's 4 digits. In this case, it happens to be 4 digits. No rule like that. You know, I could have a number, not 0.45. 0.45 is easy. I could have done like 0.143265357. I mean, I don't know what, some long number, and I'd have to convert that to binary, and it may never repeat, and it may repeat only 2 digits at the end. You know, I don't know. I don't know what it's going to do. But I took a very simple example of 45, and that one repeats. But my point about the repeating is this. It's just a side note, not important for the exam, but it's just interesting that in binary, we cannot represent that number. In other words, 45.45 cannot be represented in binary. It can be approximated. This is an approximation of it. To fully represent it, I would have to have infinite space, and I can't have infinite space, so I can never represent it. And there are also reverse examples. There are examples that can be expressed perfectly in binary that cannot be written in decimal. Just an interesting thing about math. And the interesting question, here's an interesting question for you, which I don't know the answer to, which is if there's irrational numbers like E, is it possible that they could be represented in some base that we just don't know, and then it would not be an irrational number? Well, I guess not, because
Isn't the point of those numbers
that they
the
can't
point
be
of those
represented
numbers
in any base. They can't be represented in any
can't be
base
represented
because
any other way?
they can't be represented in
Yeah,
any
but maybe
base.
they just can't be represented.
I'll give you an example. Yeah, you're right. That's the point. Now, they can't be represented in any base because they never repeat. Assuming they never repeat, then that means they can't be represented in any base.
Count in base pi, I think it would work.
What?
You might be able, if you count in base pi, I'm not sure how that would work, but
Right, that would be exactly counting in a
then
base
it would
that was
actually
not
make it 1.
right. I don't know how that would work. But here, I'll give you another example. What about the number a third? When you represent that decimally, it's 0.333. It can't be fully represented, right? Can't be fully represented. Just write 333, and eventually you run out of space, and it's not exactly a third. But proof is, if you multiply it by 3, you'll get like 0.99999. You won't get 1. So,
but if you take a third,
but if I
you
was
multiply
writing in
by
base 3, wait a second. But if I was writing in base 3, I never heard of base 3, but I could have base 3, then I could represent it. I probably could represent it exactly. I mean, yeah, probably, because it's you know what I mean. I could probably represent it exactly in base. I'd have to think about it, but base 3 would have obviously the digits 0, 1.
1.
What?
A third would be 1.
No, a third would be point something. 0.1.
All right.
3 would be 1. 3 would be 1 0 in base 3. 1 0 would be 3. But what would a third be? Anyway, you have to think about it. I'm just saying certain numbers can be represented in certain bases accurately.
Wait, if 1 0 to be 3, then wouldn't 1 be a third of that?
I think it would be 0.1.
No, 1 would be 1.
I think 0.1 would be a third. I think 0.1 would be a third. That's my guess. But maybe 0.01. I don't know. I'd have to work it out. Let's go on. I'm just giving you food for. I'm just trying to make this. Trying to point out the.
Wouldn't 0.01 be a 9?
Yeah, I think 0.01 would be a 9. So right, 0.1. I think it'd be 0.1. You just have to go back and look at this. Actually, here it should be 0.1. It should be 0.1. 0.1 should be a third, and that's it. 0.1000. In other words, that's it. And I can represent it, therefore, perfectly in base 3. Can you guys still hear me? Hello?
Yeah.
Kind of choppy for me. I'm not sure if that's me.
I know. It's,
No,
I just got a
I
message.
hear it also. It's kind of choppy.
No,
Yeah.
me too.
Yeah, so I think I'll talk slower, and my internet connection in this room is not the best. Okay, so we're done. We showed this is called exponent bias. It's biased. In other words, the number you have is biased, means it's pushed to the one side. It's you got to push it back. Okay, now we have a
What
problem.
does that mean? It's pushed to one side.
That's just the way I'm saying it. In other words, this 0 is pushed to we took the number negative 127 and we pushed it to all the way up to 0. We represent a negative 127 by the value 0. We biased it. We gave it in other words, for example, when you judge your teachers, you can give them a 10, a 9, an 8, a 7, and a 6, I think up to 4. You can't give them a 3, 2, 1, or 0. So when a teacher gets a 9, he thinks he's got a 9, but really that's a biased result. It's been elevated. It's been pushed over because really he's got a 9 out in a range of 10 to 4. So it's really, it's slightly lower than a 9. It's like an 8.5 or 8 1/4. So that's what I mean by bias. The range is changed. So anyway, how do we represent 0? Remembering any number is raised to 0. Any number raised to 0 is 1. So an exponent of 0 does not normally mean that the number is 0. In other words, how would we represent a 0? If you think about our system, if I put a 0 in the exponent, that means raise it to the power 1. If I put a 0 here, that means it's positive. And if I put all zeros here, well, I should know to append a 1 in front of it. So it should be 1 to the power 0 times 2 to the power 0, which is 2 to the power 0 is 1. It should be 1. If I write all zeros here, it should be 1. And how am I going to write 0? So the answer is they just made an exception. And if you write all zeros, that means 1. That means 0. If you write all zeros, remember, any number raised to 0 to the power. So if the exponent is 0, the mantissa. So if the exponent is 0 and the mantissa is 0, then the value is 0. They just made a rule like that. So now you could ask, the question to ask is, how do we represent, how to represent 1?
And therefore,
Right? That's your question?
will the result be 1 then? Like,
No, if I want to represent 0, I'm just going to write all zeros. And the computer is going to identify that and say, he's going to have a special if it's all zeros, then it's 0. And he's going to ignore his normal behavior. So then we're going to question, how am I going to represent 1?
How are we going to represent 1? Where? As the value, or as the mantissa, or as the exponent?
No, the number 1. I want to represent the number 1. Guy types 1.0000. How do I represent that number in this method? Anyone have a suggestion?
It could be 1 to the power of 1, or to the power of 0 even, I guess.
Well, if I wrote 1 over here, then that's all zeros. And if I put to the power 0, I'm not going to put to the power 0 here. What am I going to put over here?
That's
I'm
the
not
power
going
of
to
1.
I'm not going to put 0 here. Remember, 0 would be a minus 127. I'm going to put here 127 here. No, I'm going to put not 128. I'm going to put 120. Oh, sorry, 128. You're right. Sorry.
128 will give
no,
you
127. 127.
you
I'm going to
0.
put 127 here, and I'm going to put all zeros here. So the all zeros here is going to tell me it's actually 1. And the 127 is not 0, it's 127. But when I do my math on it, 127 minus 127 is 0, and I'm going to get 1 to the power 0 is 0. If I would put a 1, if I put 128 here, it wouldn't work because it would be 2. It would be times 2. That would be 2. 2.
Yeah, anything to the power of 0, 1.
Anything raised to the power of 0 is 1. So I'll write here 1.
Yeah, power 0 is 0.
I'll write here all zeros, and I'll write here 127, and that will give me the value 1. What is that, right? So actually, I can write 127 here, right? In other words, and if I wrote 0, wait, what is 0 going to be? 0 is going to be negative 127. So actually, it's going to be like this. I can never, what number can't I represent? I can't represent 1 to the power times 2 to the power 127. Right? That's the number I threw away. Because how would I represent 1? Sorry, how would I represent, 1 times 2 to the negative 127? I would write 1 over here, which would be all zeros, and I would write 0 over here to be negative 127. That'd be zeros here, zeros here, and 0 here. So that number I lost. I can't represent that number, but I also can't represent lots of numbers like that. I can't represent. Because at the end of the range, I lost that number. That's like the end of the range number. But I could represent, for example, a number slightly larger. I could represent 1.111111 to the negative 127. But I can't represent just 1, even smaller number. So it just means I lost essentially I'm using the smallest number in the range in the possible things that I could represent. I'm using that to represent 0. And I lost a certain very small negative number, but I don't really care because anyway, I can't have every possible negative number, every possible tiny number. And I actually gained a nice thing, which is that all zeros, it's very easy to think about. All zeros means 0. So how do we represent 1? Simple. Simple. Use power 127, or exponent, I should call it. Okay. And now, similarly, 255 represents, in other words, all ones. I don't know, actually, I think it means, and I think and the mantissa being with, I think mantissa all 1. I think so. I'm not sure, but it must be. It logically must be. So 100. If you want to represent infinity, you could write all 1s in the power, and the mantissa also all 1s. And I said this may explain why we don't use 2's complement for the exponent value, because we want to save the special values 0 and 255 for other purposes. So that's the other possible reason why we didn't use 2's complement. And we use this other system. Okay. Now, let's go on to the reverse. By the way, you guys have a class at 2:30?
Yep.
Yeah.
Yeah. So we'll stop at 2:25.
Yeah.
We'll stop 5 minutes before that. Okay. Convert the following to decimal. I don't know why we decided. I don't know why I decided, or you just have the class at this time, but I prefer it in the daytime again. I think in the earlier part of the day. Anyway,
Alternative was worse.
What?
Alternative was worse. Would be at 7:30.
Exactly. That's what I'm saying. I prefer to have it in the daytime. I don't have class at 7:30. So we're actually cheating you because you're not getting as many hours.
I think mine also supposed to be technically having an.
I didn't hear you.
I think we might be supposed to be having another class on like Wednesday nights at like 6 or something like that.
Ah,
Yeah, we have classes on Wednesdays from 6 to 7:30, and then Thursday from 1:30 to 2:30.
yeah, I know. That's what I'm saying. That's exactly, I know. I'm saying, so I should have that other class also. we'll see if needed, we'll add that in. In other words, if I'm able to get in the material quickly, then we may not need that time. Also, I can do videos that you can watch on your own time. That's part of the reason I want to do videos, actually. 'Cause I don't like, yeah.
Are you able to also maybe explain the homework a little more?
You mean homework in the theory, not in the lab?
Yeah, we're having a little trouble with it.
Yeah, I can explain it a little bit more. I mean, basically, it's very similar to chapter 6 that we did. It's just what lines to add, and you just have to, it's just, you know, it's just test questions based on those 2 examples that you saw. I did 2 examples. These are 4 more examples to do. They basically work on the same principles. I mean, you have to be creative. The point is you have to think about, okay, what am I going to do? It forces you.
We need to add more lines. There's not enough features inside the processor already to.
Exactly. All those 4 things that you have to do there, you have to add stuff to the processor in order to accomplish what you want to do. And you're supposed to figure out what to add. And you have to demonstrate, you basically, it forces you to figure, to really know, to be sure that you understand how the thing works, how the computer works, what each part does. You know what I mean? It forces you to get into the nitty gritty of what we explained in the examples that I gave you in chapters 4 and 5 and 6. It's a very good targil because it's very good exercise because it gets into the it reviews all that we learned in 4, 5, and 6. All the different parts. What am I going to add? It's putting you in the driver's seat. You are now the engineer designing a chip. What are you going to do? But instead of designing a chip from scratch, you're designing a chip. It's already partially designed. And you're just adding more features to it. I can help. I can do it. I mean, I don't know, but the goal is to figure it out yourself, and it requires time. I think what you have to say. Okay, what does this command need? What am I going to need for this? When am I going to need it? But I can try to help you guys.
And when is the homework due?
I don't know. I didn't decide yet. I'll let you, there should be dates on the.
You broke up a little bit.
What?
You broke up a little bit, so I didn't hear you.
I didn't decide the dates.
You just said.
I did not decide the dates. But soon. Okay, let me just continue here, or I just have 3. Oh, I don't know if I can do this in 3 minutes.
Because like as of now, it's due today.
As of now, it's due today. So I think somebody asked if they can have more time, and I said I'll give you more time. I can give you another few days, maybe another 5 days. But because we have more stuff to do. All right, guys, let me just, I only have a couple minutes here representing, let's say we have this number. This is now the reverse process. Let's say I have this number in a register. In other words, let's say like this. Assume, I'll rewrite this. Assume a register has this value. Represent that value. Okay. So a register has this value. What is it? Figure it out. So the 1 means it's positive. The next 8 digits are the power. Stick them in the power section. The next 23 digits are the mantissa. Notice lots of zeros. Well, okay, what am I going to do? First of all, what?
Doesn't the 1 mean that it's negative?
Yeah, I'm sorry, my mistake. Sign equals negative, yeah. The 1 means that it's negative. The power is what? Well, the power, that's 17. That's 16 plus 1, 17. 17, now we have to do minus 127 means the power really means minus 120, 110. Even though it wrote 17, it really means 110. That's the power. And what's the mantissa? Well, the mantissa, I can figure it out like this. Let me go to view, present. Notice this is the 2 to the minus 1 column. This is the 2 to the minus 2 column, 2 to the minus 3 column. This is 2 to the minus 4 column. So I wrote 2 to the minus 4 plus 2 to the minus 5, 6, 7, 8. 2 to the minus 8 column. The rest is all zeros. So all I have to do is take this number and multiply it by this. Well, wait a second, we're not done. I like this view better. So that's the mantissa. I've now figured out this mantissa is this. How did I get that? I typed it into my calculator. That's the only way to do it. I mean, there might be other ways to do it, but the way I would do it is with a calculator. 2 to the negative 4 plus 2 to the negative 8. I got this value, base 10. And I got an exponent of 100 minus 110. Now what? I'm not done yet. Now I use this formula. And I say, take the mantissa. Remember, I have to add a 1 to it. So even though it was 0, 6, 6, remember that's what we had before, 0, 6, 6, 4, etc. I'm now going to have 1, 0, 6, 6. The sign is negative, so I'm going to put a negative. And it's times 2 to the negative 110. And if I punch that into my calculator, I get negative 8.21 times E means times 10. E means exponent. Times 10 to the negative 34. And that's my answer if I had that question on a test. Now, this is an interesting little formula because what it says is if you take the sign and you raise negative 1 to the sign. So if the sign is 0, negative 1 to the 0 is 1. So that means positive. Anything times 1 is positive. But if the sign is 1, then negative 1 to the 1 is negative 1. That's going to take this number and multiply by negative 1. So there's a little formula to show you how to convert using the neat characteristic of the sign that I can put it as the power of negative 1, and then it tells me whether or not the number is positive or negative. So it's the sign times, the negative 1 to the power of the sign times 1 plus the mantissa, because I have to append the 1. This plus, I have to append it or add it, doesn't matter. Times 2 to whatever the exponent I got is. And that's what I did here, and that's what I got. So we'll stop there.
The exponent is including the sign?
The exponent is not with the sign. The sign here determined the number of the sign of the mantissa. The exponent, we determined that it was negative 127, 110, because we did this subtraction. Remember, it's always it's a biased. Even though it looks positive, we subtract 127 from it and we get a negative number. So the exponent could be positive or negative, even if this is positive or negative.
After the exponent, wouldn't it make more sense just because based on how we normally read things in scientific notation that it would first be the sign, then the mantissa, then the
Oh, I don't know why they did that. Probably for.
It also seems like we always put the bigger numbers at the end. Like we put the smaller things at the beginning of the line and then just throw in.
Right, that's true also. We tend to put it's like the Mishnah. There's some people like write these long explanations of why the first Mishnah in the Seder is brachot, and then the next one, and why the first one is baba kama, and what the order is, what the meaning of it is. So I think the Rambam writes that the real reason is because the longest one is first, and then the shortest ones are at the end. So here it's the opposite. The shortest ones are at the beginning. We take care of all the shortest ones, and then the longest ones. I mean, I don't know. I don't know if there may be a hardware reason why it may just the wiring might work out better this way, but that's just the way it's done. All right, I'll stop here. I'll give you another 5 days for the homework. I'll change the date.
Thank you.
Thank you.
Very much.
Sure, my pleasure. Stop the meeting.